I mean, at
You don't mind, right? Yeah.
Oh,
Okay.
it's fine. At first, I thought it was, it's just like a normal proof, but then
Sure.
I posted on Piazza and it has to like using regular expressions in particular.
Yeah.
So I've never done like structural induction in that. In that realm.
Let's see. Let E be a regular expression by using the definition of show how to construct a regular expression. Okay, so okay, let me think for just a moment what the answer to this would be if it's so I can definitely think of a complicated way to do it. Show how to construct a regular expression ER. Oh, I see. This is just, you have to pick a particular regular expression.
Right, just to show that.
Such that the reversal of the expression is the same as the reversal of...
Basically just showing like language is closed under reversal.
Yeah.
Using regular expressions.
So which lecture's regular expressions? Let's see. I want to just see what he's told you guys you know about regular expressions.
Yeah, I think it was lecture 11 or 12. No?
Yeah, I see it. It's January 22. So... Okay, so where's his regular expressions bit? So it should basically be sufficient to prove that this holds for all of the operations, right?
Right. So like just do like case by case.
Yeah.
So yeah, that's like so the base cases are fine.
Yeah.
But like my confusion is like
right.
for
So you have to assume that it is inductive, right? In the sense that you're kind of like, if you've done the base cases already,
right,
you can assume that your regular expression on each side of the so assume that as long as once you've proven these base cases, you can kind of assume, okay, well, each regular expression on each side of the like union, let's say, has, so if both of them are any of the base cases, then the reversal thing holds, right? So let's say, so here's what I'm trying to say. I'm going to try and use the same language he uses. So certainly, let's just think of the union operation. I'm not sure if he wants it this level of formality, but let's just do it this level of formality. So from A, the regular expression is A. Okay, so let's assume that it's pretty trivial, these base cases, right? So you can do like 1, 2, and 3 easily.
Yeah, be.
But there's kind of like a base case for the operations as well, which is, let's assume that for their base cases, we're going to assume that we want to show like L. How visible is this? Let's try black.
Yeah.
Sorry. So I'm gonna try and. These are all new, which helps. But let's find the most readable color before I continue.
That looks better.
That does look better. Yeah, they look. And then this is a new red, unlike the last red. So let's see.
No.
Red's the worst. Okay, I think black. Let's go with that. It's kind of what I expected.
maybe the light,
So
is it
the
possible?
light's so annoying. Yeah, so I
Just
used to.
one side.
The problem is I don't think I can do just one side off. I can dim them a bit. Let's try that. These don't work right. This dimmer sucks. Okay, well that did nothing. I'm not gonna waste much more time on it, but I'll try not to write where the bar of light is. Let me write a little lower so that, or a little higher. Yeah, that's more readable. Okay, so we have like LR1, LR2.
We're assuming that R1 and 2 are like regular, like that's gonna be from the.
So let's just
lines.
assume actually that let's assume one way to deal with base cases for union is to say assume that R1 and R2 are like atomic in the sense of they're from 1, 2, and 3. So see the so the base cases right before for R were like R equals the empty set, R equals the set of just, sorry, LR being one of these is kind of like your base case, right? Where it's epsilon. I do epsilon backwards, yes I do. Which way is epsilon?
This way, I think.
This way, okay. How did I forget epsilon? I draw so many epsilons. Okay, and then like A, right? These are like your base cases.
Right.
Well, let's assume that R1 and R2 are from the base cases.
Like, is it possible that they're not from the base cases? Like.
Yes, but we are trying to deal with a base case for union right now. And this might be actually a little more formal than he's looking for. I might shoot him an email and ask him and then like put a correction if this is too. I'm being super formal right now. I'll let you know in the post about the video how whether like this is the correct amount of formality. So basically what was I going to say? Right. So now we want to show that if I union two regular expressions together, that this so I'm trying to prove that this equals, L of R, so this is its own language. This equals what? Let me look at union really quick. Make sure. R equals R1 plus R2. So we have R equals R1 plus R2. So that should be, so if L equals L1 plus R2, then we can essentially also write it like this. Is this off? No, this is fine.
So what does it mean to reverse an expression exactly? Like what's R1 reversed?
Yeah, that's kind of what I've been looking for, because he doesn't define. That's what's got me a tiny bit confused on this question, is I haven't seen this notation for this kind of thing before. Let E be a regular expression by using the definition of regular, show how to construct a regular expression ER. So the reverse of an expression is, yeah, he doesn't really define that. The reverse of the language is reversing every string in the language, right?
Yes.
Reversing the expression is kind of similar then. but the expression is a set. The expression, let's see, how's he defining all these things? Where does he define reverse in the first place?
Oh, it's like lecture 1 or 2.
I think so, yeah. I want to see the exact definition of it.
I think also there was a Piazza post about it. Is it like the reason he put like the superscript in parentheses that so that he just means it's just a different expression that gives you the reverse of the language, so we shouldn't be treating the expression as a string and flipping everything. That's I think what he mentioned in the Piazza post.
That's correct.
Yeah.
You should be reversing the components of it.
Right.
Yes. Like, if you have unions of a bunch of things or intersections of a bunch of things, the reverse of the expression is the reverse of each of the components.
Yeah.
Right? Intuitively. But where that definition is, I'm not sure. You said he put it in a Piazza post? Let me read his Piazza post and see if it's clarifying for me. Let's see. So, question 1 proof. Can I just show that the regular languages are closed and reversal and then use theorem? Right. So, I guess I would just kind of do it like this. Given how he wrote it, it is a slightly confusing question to me, which is probably just my misunderstanding. But anyway, so the way you can do it from here, though, is, so imagine that these are from this set. Then this is sort of your base case of proving this equality, right? And then you could just do it by brute force. It's basically trivial, right? Because because if I try like these are both empty set, well then their union is empty set, and here empty set, reverse of empty set is just empty set. So you're gonna have union of empty set with empty set, and you're gonna have union of empty set with empty set reversed.
And how would that generalize? Like if say R1 and 2 they're not atomic, like
right.
how
So this is the base case for union, right?
Yeah.
And then from here, now what I want to say is assume that for, any two expressions with at most, let's say, n of the other operations, that these are atomic. So basically, if you have an expression with n unions, intersections, or whatever, total, then it's atomic. Let's assume that. Now, I'm going to prove that if I put a union between that and another thing with the same property, that it's still atomic.
Okay. So like
that it's still the same as its reversal.
So induction is going to be on the number of operations.
Yeah, that's probably what I would do.
Okay.
I would do I would do induction on the number of operations.
Okay.
And you can do base cases for each of the operations, and then just say assume that we have n operations of, what are they, union, intersection probably, and one more thing, and star. No, union, concatenation, and star.
Yeah.
Right? Yeah, of course. So union, concatenation, and star. So I'm going to do the base case for concatenation, I'm going to do the base case for star, all of which are very simple, right? And then you're going to be like, okay, assume I have at most n union concatenations and stars of, basic regular expressions. I'm just going to call these like atomic, even though there's some different cases. Then if I add any one of those things, if I add a union, a concatenation, or a star of any of those languages, so either a union of two languages with n or less let's call these operators, and let's call these atomic. So if I have two regular expressions union together, each with n or less atomic things, then it's fine. If I have two with n or less atomic things, then concatenating them together is also fine. And then if I have one with n or less operations and I star it, then it's it's still equal to its reversals in this sense. Does that make sense?
Yes. So like we basically like doing induction with an induction for like for each case.
So you have a base case for these, right? Just proving these are the same as the reversals. Then you have a base case for let's see. Actually, that's already your base case for. You don't really need to do this. Sorry, I'm gonna make this much easier. This is let your base case be 0 applications of union, concatenation, and star, which is just these, right? And now you're going to say, assume that with where R1 and R2 have, where LR1 and LR2 have at most, are defined from these with at most n unions, intersections, and stars, we show that the union of 2 such languages, the concatenation of 2 such languages, or the star of 1 such language is still the same as its reversal.
Okay.
That the reversal of it and the reversal in the interior, like whether the reversal is in the interior or exterior, it's going to be the same. That sounds like how I would do it, yeah. It's the first way that comes to mind. Does that make sense?
Yeah.
Cool. I don't think it'll be that arduous. It's
I mean, I
mostly
think what
just
was confusing me was like to reverse an expression.
And it's kind of weird because it's pretty important to say that these don't have exactly n operations.
Mm-hmm.
You kind of have to be careful and say like they have at most n of these sorts of operations, because otherwise the induction wouldn't cover things like languages that have n+1 operations, right? Because then they'd both have n, and so their union would have 2n+1 operations. So you need to allow for them to have n or less. Like let's say we're just using union, okay? If these both have exactly n unions, now together they have 2n+1 unions, right?
Right.
But if this can be like empty, let's say, then if this can be atomic and this can have n, then together they would now have n+1. But so this next, essentially your inductive step doesn't cover the n+1 case.
Right.
It covers the n+1 to 2n+1 cases all at once. Does that make sense?
Yes.
You could also treat 1 as atomic, but you don't really need to because you have your inductive hypothesis, and so the reversals are going to be really easy to handle.
Right.
Does that make sense? Yeah. It's a bit weird, but okay. Does that make sense for question 1? How to kind of go about this, or do you still have any questions about it?
How do you do the like inductive part?
Right.
Like,
So this is the inductive part, right? So there, if you look at the lecture notes, right, you've got 1, 2, and 3 of your kind of basic, let's call them atomic regular expressions.
For like we accept that as regular, right?
Yes.
Okay.
So first thing you want to do.
And
so,
any reversal of those.
So what I'm going to do
would also
induction on is 4, 5, and 6 are like operations, right? They're the union, concatenation, and star of languages. So what I want to show now is that you've got this kind of reversal equality. No matter
if that
how
holds
many.
True if that holds true for the 3 things, then we're like done, right?
Yeah.
Okay.
So what I want to show is that for every regular expression, this is going to hold, and what I'm going to do induction on is the number of unions, concatenations, and stars of these kind of basic regular expressions. Okay. So my base case, is where I have 0 unions, concatenations, and stars.
And then you know
in which case I just have one of these, and then you prove that they're all the reversal of each other, which is like
trivial.
Pretty trivial, yeah. They all follow from just the definition of reversal.
Okay.
Now I'm going to assume that for that I have 1 or 2 languages. Let's say 2 languages, R1 and R2. I mean LR1 and LR2. That have that their representation, let's say, has at least that there's at most n unions, concatenations, and stars defining those languages from R's like this. Okay. Well, now I'm going to prove that if I at most, not exactly, right? Okay. And now I'm going to prove that if I union those 2 languages together, that this equality holds true.
Okay, so it's not like you have to then do, now assume that we have n+1 as the most operations and then prove that? Like
no, because so think about it like this. We know by the inductive hypothesis, we have that I can actually take these out. by inductive hypothesis because these have n or less unions, concatenations, and stars.
Okay.
And our inductive hypothesis is any such language has the equality of like this, like
Like
L R1. Our inductive hypothesis is going to let us do this.
Okay.
Right, because these languages are of sufficiently small size to apply this
you
rule.
can do that.
That you can
Got
do
it.
that, right?
Okay.
That's the entire inductive hypothesis, right?
And the reason that because you can just put the reversal across the union,
Right.
like by definition.
Yeah.
Okay.
By definition of
And
reversal,
then
I
the
think.
inductive
I'd have to look back at it like
Sure,
the first
sure.
lecture, but yeah.
Yeah. Okay.
Does this make sense?
And then just a similar process
Yeah.
for star and
For
concatenation.
star, yeah, for star and concatenation.
Okay.
It's similar things.
So like concatenation, you'd be like L of R1 concatenated with L of R2 all reversal, and then show that that's equal to like L2R, L1R.
Yeah, so you're gonna have, let's see, L1, L2. This is shorthand for me for L of R1,
Sure.
L of R2. And so I want to prove what? That,
Like that whole thing reversal.
this whole thing reversal. So this itself is a regular language. So I want this
Uh-huh.
equals,
L2R, L1R, or no?
yeah, that's the impression I get, is you have to,
Or is
because
it-
like, it's in the interior of the language, but
Wait, is it L2R, L1R? Is it L2R1 or on the right?
no, you're right. It's the whole thing reversed, because it has to be. This is not it.
Oh, okay.
Right. It's got to be this, right?
Okay.
Right.
Sorry, what's L12? Like the shorthand here.
This is L of R. This is L of R1.
Okay. And then L1.
L and then L2 is L of R2.
Okay.
And so this is their concatenation.
So like when you take the reverse of that, what's that exactly? Like L2 super.
So this is the reverse of all strings in L of R2. So wait, let's see. Sorry, no. So one is the reversal of expressions themselves. So actually, I think what it really is
is that like L2R?
it's really actually. I shouldn't use this shorthand. Give me a sec. Makes it more confusing. Okay, so I'm going to define a new language as LR1, LR2, right?
Mhm.
And one of my things is going to be
Reversing the whole thing.
reversing the whole thing, and I'm about to go off. No, I think I have a little more space. And then my other one is going to be, these are going to reverse, and then it's interior, right?
Mhm.
So it's L of R2 reverse. L of R. I can't do the shorthand. Here's why you can't do that shorthand,
why
right?
is
It's
the
because I need to
R-
get into the interior.
Why is the R on the inside and not the outside?
Yeah.
Because that's what we're trying to prove, right? The whole point of this proof is to show that the reversal of the language is the same as the reversal of the language of the reversal of the expression. That is the question in English.
Mm-hmm.
Let me go to the problem set again, just so I can read exactly. Right? That's what he's asking. Because one is reversing the expression, which was the thing that people were confused about on Piazza. Right? It's reversing every string that defines the every like string in the regular expression. You're not reversing the expression itself. So here's how I want to explain this, I guess. If I have like 0, 1, union 1 is my regular expression. So the language is the set of these two strings, right? And the reversal then of the language is going to be like 1, 0, and 1, right? It's going to contain these two elements. But the reversal of the expression is going to be something slightly different. I mean, it's going to end up with the same strings, but the way I think you would want to evaluate the reversal of the expression is it's not, what it is not equal to
Is 1 union 0, 1.
what was it? 1 union 0, 1. Exactly. You don't reverse the expression,
Sure.
right? You apply reversal here, and what it is equal to. Actually, I should leave this up as an example of how not to do this, which is 1 union 0, 1. I'm going to put parentheses so it's more readable. Maybe that made it less readable. Let's see. 1 union 0, 1. So what I really want is, what this is equal to, is 0, 1 reverse union 1 reverse.
Okay.
Right?
Yeah.
You have to distribute it within the expression. So that's basically what's happening. That's all that we're trying to prove for regular expressions in general.
So I'm confused, like what, like are they equal, like L, R2 all to the power, or all raised to R, or like super
So
R, or
what the
when-
lecture
when it's
said-
inside and outside of, what's
So what the
difference?
lecture said, right, is if you take two languages,
Yeah.
wait, let me double check. I want to make sure I'm exactly on point with how the lecture describes these things. So in point 5, the concatenation of two languages of regular that are derived from regular expressions,
Yeah.
right, is let's see, is the language defined by every string in both of them concatenated together. It's R1 plus R. So the language of R, if R equals R1 plus R2, or sorry, R1,
Just like R.
R1 concatenated with R2 is the language of R1 concatenated to the language of R2.
So like in that sense, like is this true? Like are these two things equal?
That is what you are trying to prove.
Oh, okay.
That is what this induction is for.
So if we're trying to prove that, how can we just go from that to, like I don't.
So that is what we're trying to prove, but this is what we have from our inductive hypothesis. That
Oh, so this would be equal to L of R2 to the R, L of R1 to the
so
R.
you can take what you
and
can do.
then,
Yeah,
like,
because of our
there's an
inductive
intermediate
hypothesis,
step.
I can take these out. Right? Of their
Wait,
language.
because of the inductive hypothesis, you can take that out, or
Of,
it
I can take the
starts-
R out of this and the R out of. They start like this. This is what I'm trying to prove.
Oh,
Okay.
I guess I'm wondering if you apply the inductive hypothesis to get the right hand side, or if you start with L of R2 to the R, L of R1 to the R, and then you apply the inductive hypothesis to bring it.
You
inside.
start with it.
Okay.
Let's say you start with either of these and you want to get to the other using the inductive hypothesis, right? Because you want to show they're equal. So let's say I started with this and I want to show it's equal to this.
Mhm.
What I can do is I can apply the inductive hypothesis to take the
Sure,
reversals out. Then I take the reversal away from both of them by swapping their places, right? Just by definition of reversal,
Oh,
right?
okay.
And you're done now. That is
Okay.
inductive step
Right.
for reversal.
Yes.
Right?
Okay.
Yeah.
And
And
just
so
for
I'll leave
concatenation,
star and for concatenation.
Okay.
And I'll leave like union and star to you guys because I think that they're
Yeah.
not that hard, right? Like this is
Star,
like literally
but
two
star
steps.
only involves like one language, right? You don't
Yes, the star would involve
Okay.
one language with as many as n unions, concatenations, and stars. In
Okay.
it. I feel this question is not hard; it is subtle.
Yeah.
Does that make sense?
Yeah,
Like
yeah, yeah.
the technical aspect of this question is very simple, and it should not be a long proof at all,
Right.
right? But what he's asking is subtle. that's why it took me like a minute. I was just like reading. I was like, oh god, this is. Because I've actually never seen someone do reversals of regular expressions, but I mean like, but yeah, I mean it makes sense as long as you define it like this, right?
Wait, is the
This is the thing people were confused about because they didn't know how he was defining reversal of.
is the
regular
union
expression, but-
step not already done, or
I mean, there's like one step involved. So this is what we want to prove. How do we get from here to here using the fact that we have this assumption?
okay.
Right, like
Sure.
I won't give you the very, Does that make sense?
Yeah.
Okay. It's just as easy as the other one.
So like all three cases, they're gonna have the same inductive hypothesis.
Yes.
Basically.
So I was thinking it was going to be separate ones, but I batched them all together to make it easier, right? Because I can just say, okay, there's as many as n of each of these operations combined.
Right.
And that covers the case where there's n stars, there's n unions, there's n concatenations, or there's some combination of them. And then I don't have to worry about it. And my base case is super easy where there's 0 of these, and so then it just reduces to the...
To the
Yes.
common ones. Okay.
Yep.
Okay. Can we possibly like see how the clean star hypothesis, like claim is gonna look like, the one that we need to prove, just like these two, like.
Yeah, so you're going to have L of R1 starred, and you're going to have, L of...
Do you have L of R1
L-
star?
It's
R,
L of R. I mean, you don't need an R1 and an
Okay.
R2 anymore, right? So it's L of R starred
R.
reversed
So like the reverse is
outside the
outside
star.
parentheses of the star, right?
Yeah.
Okay.
Because we need to take the reversal of the language, and the language is defined by some other language starred.
Star. Yeah.
So the R is on the outside of the star, right? Because it's L of R.
And you want it on the inside.
Right, so we're going to end up with something like, let's see. So it's L of R star reverse. And what's the other? And the other one is what?
L of R to the R star? Like star outside? Like,
Exactly.
Yeah. Okay. So it's just a little trickier because the star is in the exponent
Yes.
instead of like
Yeah.
in
This is
in fixed notation.
Probably the toughest one, but it shouldn't be
clean
that
star?
scary. Yeah, I mean, it's also only a couple steps. You just need to find why you're allowed to move the R around in certain places.
Right.
Certainly, this gives you one way you can
And because
shift
we
the
can
R.
just take that as given.
This is your inductive hypothesis.
How does the
Because you've proven that this equality holds true for strings of this form, right?
Mm-hmm. You're right.
Where,
And then
which is
that-
the
and
zero
then L
union
would be
concatenation
any
star case.
combination.
Right.
So
And now I'm going to assume that for,
Okay.
a language R1 and for any language R,
Mm-hmm.
with n or less unions, concatenations, or stars, this equality holds.
Can
That's
we-
my inductive hypothesis.
I know that this is like several weeks ago. Can we go over what the Kling star like means exactly?
Yeah, for sure. The Kleene star, I'm not exactly sure how he defined it, but it's
I guess
always
like more
the same
more like
thing.
informally.
Yeah.
instead
I
of,
mean, informally, if I take the star of something,
Uh-huh.
this is, for regular expressions, this is the
It's like
for the language
infinitely.
of this. So this is a regular expression, right? The
Mhm.
language of this regular expression is the union of, let's see, it's
like any combination.
it's going to have 0, 1 to the k for all, so it's, here. This is actually formally how I can define it. So the language equal to, I'm going to erase something because things are just getting a bit crowded. We're good on all this
Yeah.
stuff? Okay. Great. Okay, so the language of 0, 1 star is equal to the set of all 0, 1 to the k for, are you guys familiar with this sort of set notation? So basically, here, I'll finish writing it and then I'll explain. Where k is between 0 and, actually, you know what, best way to put this is? Natural numbers contain 0, by the way, so let's see, in my mind. K is an element of the natural numbers. Okay, so this sort of notation is a common set notation where we say this subject to this constraint. So it's like all things of this form such that this is true.
Mm-hmm.
So it's all strings of this form such that this is true. So this includes 0 though, which means that you take 0 of this, it's going to have the empty string.
Mm-hmm.
Right? So it's the empty string, it's 0, 1, it's 0, 1, 0, 1, it's 0, 1, 0, 1, 0, 1.
Got it.
The weird thing for this one is that one is the reverse of the whole star. The other one is the reverse of the initial segment before you apply star.
Right.
And you have to prove that that's
That they're
equivalent.
equal.
Oh.
So that's the tricky, that's where you can get tripped up
okay.
in star.
So now it makes sense intuitively. Okay.
Yeah.
Because if you flip the.
So that, yeah. So
Got it.
intuitively now, like, maybe understand it, and I
Yeah.
don't think it'll be too many steps to polish off.
Okay.
Oh, you can throw me my sweatshirt so it's not.
Oh,
gone.
okay.
Then give me my jacket and sweatshirt, and I'll put them. elsewhere. No problem. Okay. Cool.
Sorry.
Plenty of time. So does that make, does question 1 make sense now?
Yeah.
Yes.
Let's see. So the other 2 questions are pumping lemma questions, right?
Mhm.
How do people feel about the pumping lemma? That is usually the
Guessing.
that's the most challenging part, I think, for people to understand. Like the first really challenging thing for a lot of people. Okay, so maybe I should just go over the whole thing from scratch. What example? What example has he used? Let's see. Okay, so I'm going to use an example from last year's formal languages, actually. Okay, so strings such that the length of x what is usually used for string? Is it W?
Yeah.
Sorry. So all W such that length of W equals 2 times K for K in and is this regular?
Yes.
This is regular. Let's try something else. I'm going to do a couple different ones. Because the third question, I want to make you guys like guess a bit, because the third question doesn't tell you if it's regular or not, which is part of the difficulty of that problem. It's just regular.
Now we're talking.
Wait, why was the other one regular?
Sure.
Sorry.
Yeah.
Is it 2 times?
No, it's good.
Like, how do you immediately know? Like, is it just
Yeah,
when
no
it's like
problem.
finite or?
So, it's not finite. It's definitely not finite.
Oh, yeah, sorry. Yeah.
Because it's asking for a counter, essentially. And what I'm going to do is I'm going to build a DFA that does this. So this is an accept state, because 0 is one of the options for K. So like 0
'cause it's
strings
just
are accepted.
bouncing. Okay.
And then I'm going to send it between 2 states, one that's an accept state and one that is not.
Mm-hmm.
And 0, 1, 0, 1. It doesn't matter what the alphabet is. You just put every alphabet symbol on each
Mhm.
transition, right? So,
Okay.
Good.
Sure.
but yeah, that's how you know that one's regular. Trickier.
not bounded.
So it's the last one was infinite too, right?
But it was bounded to certain.
It wasn't bounded, right? Because no matter what number you said to me, I could tell you a bigger length string that is in the language, right?
Mhm.
So there's no bound on the length of the strings in the language, and this is the same property in that respect.
I guess the last one was strings that have a length that's an even number,
Mhm.
if it could be 2k, or
Right.
but if it's 2 to the k,
Mhm.
then it can be there's no limit on what the string could be.
So so rather than trying to build a machine explicitly, this one's much harder. So let's just take like a vote of intuition of whether people think this is regular. Who thinks this is regular? Nobody. Okay. Well,
Seems like
that's
most
good.
of the exponent ones that we've had are not regular.
Oh, I see. Has he already done some exponent ones with you
Well,
guys?
on the
I mean,
homework,
like-
the one we have to prove that k to k squared is regular.
But this is different.
Well, this is the
That's it.
opposite.
Yeah.
of this.
Let me. I'm just double checking to make sure. I know what 3 is because I have to grade 3, and it's gonna be ugly. Oh yeah. This is very similar. It's okay.
Well, this
It's different enough that I'm okay with it.
the one
so-
in the homework is just it's all A's. This doesn't have to be all A's.
Yeah. This is actually harder potentially. But they're basically the same proof. So. Okay. So who feels like they understand the pumping lemma super well?
Well, I don't know if I would say super
Okay.
well, but I understand, like, essentially what you can't use it to prove that something is regular,
Right.
but what you can do is you can use it to do a proof by contradiction to show that something isn't.
Right.
Where you want to choose y equals, like, some element to, like, some other one, and then pick I such that you arrive at a contradiction
Mhm.
for the, like, in this problem it would be the k and the k. You want something such that 2 to whatever the new exponent is doesn't satisfy k is included in natural numbers.
It's a good high level like understanding of it. Let's get to, can I write this any higher? Not really. Okay. So let's do step by step how does the pumping lemma work? The easiest way I've found to understand it for most people is through a game against an adversary. Did he do it that way at all?
Yeah.
What do they name the adversary? I want to use the same one. Some people call it the devil, some people call it the
Oh,
adversary.
he just called it the adversary.
Okay, so we're going to call it A. So A. And A is going to pick K. Right? So A picks some K. Then what are we called? People? I don't know.
Us.
With people.
You for us. Oh, that looks like union. Never mind. We're people now. Okay. What do? We pick. So you think of this as a game, basically, and you can win the game if this is proving this is not regular is essentially you winning this game against some adversary, no matter how smart they are. I think we can both admit that there's some chess situations where even if you're playing a grandmaster, if you have all your pieces and they have their king, they can't win. This is supposed to be a similar situation. We're gonna prove this is not regular by showing there's no way the adversary can beat us if we use a certain strategy. So we're gonna pick a string. Let's call it W, right? Pick W, and pick Y such that length of Y is greater than or equal to K. This is not big enough. Let me write it there. And more this direction. I'm just gonna push it all because I know I'm bordering on going off the screen. So A pick K. P pick the string W. And
These are two different words, or are they?
This is a string. What pick? Here's what I should say. Such that two things. Y is a sub. Let me put like between your steps and their steps, I guess. Okay, so this is one big step with like various lines. And Y is a substring of W. And Y, length of Y, is greater than or equal to K. I don't want to reuse W. UV.
For a substring?
For the breaking up of Y, what did he use in class? Do you remember?
He was using A, but it was only for something that was A. He
Okay.
used W's X, Y, Z.
UV. I'm gonna use UVZ. Actually, that'll work fine. Okay, so adversary now breaks up W into UVZ, i.e. UVZ equals W. Oh, sorry, Y. Breaks up Y into these things. Big difference. And then player picks I. Okay, and how do you win? P wins if and only if pick. I don't want to just say this is. There's actually a better way to represent this. I remember how I should read it. X, Y, Z. So I shouldn't reuse Z. W. I don't know. Let's just use something entirely different here, because otherwise I'm going to get confused a bunch of times. So this is just A, B, C. Is that okay?
Mm-hmm.
I'm thinking the way I did it last year, but he used different letters for different things.
So I
So
didn't
I'm-
see their characters or
Oh, right.
strings.
He uses A, B, C for characters. Yeah, that's a problem. Okay. Let's call these. What are letters I typically don't use? How about
NPQ.
U, Q, V? Actually, you know what I want to do? Just to make this even more clear, what this part is supposed to do, I'm going to make this L, like this fancy L.
Okay.
If you've seen that before in math stuff. Cool. Let's just, it highlights the importance of that part, I guess. And it gives me another letter. So you want to pick Y. You actually want to pick X, Y, Z. Right? Such that W equals xyz. So this is actually, and this is a simplification of this step too. I'm going to erase this and write it in this cleaner format because I don't like how wordy this was. Pick, oh, that's not what a P looks like. Pick U, L, V, such that U, L, V equals W, and size of L is greater than or equal to 1, right? Is that right? Yeah. That was to be non-empty. So I forgot that condition. Okay. Does this seem to mirror what he said in class?
Kind of. Except for the third step. Yeah. That's not included at all in what he says.
Okay. Let's do it this way and see if this makes the situation clear. Then I'll take a look at his lecture notes, see if I can describe why thinking of it this way is the same as thinking of it the way he put it in the lecture. So, P wins if and only if X, U, L to the ith power Vz is not in L.
In all other cases, A wins.
Yeah. Okay. So let's see why this is why does this prove anything? Like this just seems very arbitrary, I would say, at the outset. It's just like, okay, I don't know why. A, I don't know why you're breaking things up into the way you're breaking them up. B, I don't know why I or the adversary picks a certain part, and I have no idea how they intuitively match to proving a language is not regular. They seem very different. So let's walk through step by step. So basically, what you're trying to show is that the adversary in this situation is trying to build you a machine that accepts the language. So you've been given, there's this language to start, I should say. Right? So we start with some language L. And the adversary's goal right now is to show you that L is regular. That's what he's trying to do, okay? So what he's going to do is he needs to, if it's regular, he should be able to build a machine that accepts it, right? Accepts exactly the strings in the language and nothing else, right? Because by definition, a regular language always has a DFA that accepts it, okay? So he's trying to build that DFA. Like, think of it as like, professor asking you guys questions, right? Like you have to, like the adversary is essentially being asked to show this is regular. And we're going to show that no matter how hard he tries, he's going to fail. And because he can't build a DFA that that accepts this language, it must not be regular. Yeah. Because we're assuming the adversary is kind of like super smart, all powerful. Like if he can't build it, if it's impossible for him to build it, it doesn't exist, and thus it's not regular. That's the game that's happening here. So what is pick K? If he's trying to build a machine, what is K representative of?
Yes.
Like why does he have to pick a K? What part of building the machine is this?
So number of states.
Yeah, that's exactly it. It's finite, right?
Yeah.
So like the DFA he has to build is finite. So it's got to have some size, right? But we're going to assume we don't know what he picks, right? Because he's going to pick whatever is best for him. Okay? So we don't know what he picks, but we're going to have a strategy that no matter what he picks, shows that his DFA fails. Okay? So now what we're going to do is to show that the DFA is wrong, I just need to come up with one counterexample for his DFA, right? The problem is I don't know what DFA he's going to build in advance. I'm trying to show that, no matter what DFA he builds, it's not going to work. So I'm trying to build not so much, so I'm going to pick a string that no matter what he picked is going to work with this. And actually, yeah, good. So you pick a W, some string, and it's got to be certainly at least size k, because you're going to break it into 3 substrings, where the size of this middle portion is greater than or equal to k. What importance does this have? That we would have a what's the importance of this machine has k states, and this has size greater than or equal to k?
Can you use the pigeonhole principle?
Yes. Yeah. So I'll stop you right there, and we'll go to you guys. Like, why is pigeonhole principle important here, and why am I making sure that this part's greater than or equal to k?
Pigeonhole is, but it means that that part has to loop around.
Yes. Pigeonhole principle is just to say that I can't fit n plus 1 pigeons in n holes. It's just like this mathematical statement that, yeah, if you have more pigeons than holes, then one hole must contain more than 1 pigeon. So the important thing, though, of why k is sufficient is because you start in some state, right? There's some start state. If I have a string of length k and I read it, how many transitions must I do? K, right? So I started in the start state. How many other states are left other than the start state? So the machine has k states, right? So other than the start state, how many states do I have?
K minus 1.
Right. And so if I take k transitions, I must be in some state twice, right? Does that make sense?
Yeah, so there must be a loop.
There must be a loop within this substring y. Like there's this substring x or z, they could be empty, but I know that at least in this middle portion, there is a loop somewhere. You're going from a state and getting back to itself in some number of transitions. Why does the adversary get to pick this next part, though? So now the adversary gets to break up y into 3 pieces, such that, L is non-empty, but u and v can be whatever. Okay? So, I said w again. This is wrong. I apologize. Cool. This is y. Super confusing. Y. Okay. So why does the adversary get to pick this? So what do we know about the machine? What's all we know about the machine after these 2 stages? There's a loop, and then it has k states. We really know very, very little about the machine, right? So we know there's a loop in here, right? Where in y is the loop?
Oh, no.
Like, because the loop could be, if I have this string y 0, 1, 1, 0, it could be that I go here, here, and then here I'm stuck in a trap state, for example, and then I just keep looping. Or it could be this whole thing is a loop, and so if I keep writing this, then I loop. Or it could just be that 0, 1 is the loop, and then 1, 0 leads you somewhere else, right? I made this substring where I know there's a loop, but actually I don't know which substring of this substring the loop is in. I'll draw some specific examples to show this point. Oh, I'm off the screen. That's bad. Okay, not much board real estate left.
You can move the chair.
I think I'll move this and just go lower. Okay, so we're going to all the way down to, let me just draw a line for myself. Here-ish. Okay, that's a lot of space. So let's draw a DFA that loops. I don't really care what the accept states are, I'm just trying to talk about loops. Sound fair? Everyone can forgive me for not drawing accept states. So this is 1, this is 0, these are every other line 0, 1. Okay? So if I gave you a string, let's say that I don't know what the adversary built. This is an accept state, it doesn't really matter. But. So this is the adversary's machine. All I know about it is that it has 3 states, right? So let's say that I pick x, y, z as, I'm going to have x, y, and z be such that x equals empty string, as well as z. I'm just going to have both of these equal empty string just to simplify the example, and I'm going to have y equal 0, 1, 0, 1. Okay? That's on the screen? Yeah, good. Perfect. So, this has a loop in it, right? We know that. Which characters, though, are part of the loop? So, if I look at 0, it goes here. And then 1, it goes here. 0, it goes here. And 1, it goes here. There's actually 2 loops in this one. This part or this part are both loops, right? Now I'm going to modify the machine and use the same y. Let's make a different machine. One that does the following. So it has, let's say this, which loops to itself on 1, and then it's going to have a bunch more states that it goes to by both symbols. Let's see. How do I want to do this? Oh no, this machine's too big though. Give me a sec. So it can have 4 states though. That's fine. And then this is like a trap state, let's say. Okay, so these are led to by every symbol. I'm not going to write 0, 1 next to each one. So what happens if we use the same y here? Once again, I know there should be a loop, right? Because I have at least as many characters, at least as long a string as the size of the machine. I start here, I go to here, the 1 loops me back to itself, then I go here, then I go here. Where's the loop? Just this character.
Yeah. So I guess it's because in the pumping lemma, you just have to show that there's one factorization such that for all y, the new word is included in the language. So then, to contradict that, you just have to show that. Well, for the actual definition, you only have to show there exists one factorization. So then, for the contradiction, you have to show there's no factorization.
So yeah, exactly.
So that's why they get to pick it.
Yeah, they get to pick it because we don't know where the loop is.
Yeah.
But what we're going to say is we constructed y in such a fashion that no matter where in y the loop occurs, it's a problem.
Yeah.
Does that make sense? So when the adversary picks where the loop is, it's essentially we're essentially giving the adversary more power than they should have, right? Because they get to see this. The adversary just gets to say where the loop is because we don't know where the loop is, and so we have to assume a worst case scenario. We have to be able to show that no matter where the loop is, this is a problem.
Okay.
So, and then we pick an I after he separates makes the separation.
Yeah, because again, for the normal definition, it should work for all i's. So
Yeah.
then we just had to.
Once he tells us where the loop is, he has basically built his machine. He's stuck. Like, this is the machine he has, and now we're going to say that, well, okay, you put the loop here. If we use that loop this many times, it's a problem. So how can we use this structure to prove that this is not regular?
That's where I get confused because I can't see a situation where you're going to get 2 to some power such that that new exponent is included in the natural numbers.
So I'll just say that the trick is to focus almost entirely on I in this situation. Okay? So notice that the characters don't matter in my definition at all, right?
Yeah.
Which character it is doesn't matter. It's all about the length of the string. Right? Okay. So he's going to pick some k. Sure, whatever. We're going to pick some y of size at least k. In fact, let's just make it let's just make it the whole thing. We'll pick a w that is k ones, let's say. So my w is going to equal k ones. and my y is actually going to also equal k1s. I'm just going to ignore x and z. I'm going to make x and z empty. Okay?
Like just generally, like when you prove them, like is that how you think about it? Like you just focus on the.
I focus on this. Yeah, I focus on this game. I think it's the easiest way to think about it, but it's important to understand why this game proves what we're trying to prove,
And
right?
like in terms of like the three components of W, like which one do you like?
Oh
Is it
yeah, the
just
biggest
y?
focus is on y. But here's the reason the other things do matter. You need to use x. You need to use x and z in certain situations, and I'll actually do an example of those in a minute. Sound good? But this one you can kind of drop x and z. In other examples, you actually can't. You
Wait.
need them.
But so once the adversary has picked I, are we or K? Are
Mhm.
we fixing K?
Yes. From then on, k is fixed.
But then shouldn't you be able to choose any I not equal to 1? Because then, like, the length of your word will be bigger than 2 to the K, and then it's not. K.
What if it's 2 to the? So okay, sorry, I shouldn't use the same k here as I do there. This is some constant. It doesn't matter what. I'm gonna call this m instead.
Okay.
Sorry. The language is not defined with respect to the machine. Those are not the same thing.
Okay.
Yeah, yeah.
Okay.
This is any m
Yeah.
in.
Okay, that makes more sense now.
Yeah, sorry.
Okay.
Not enough letters in the English language. Oh, crap. I'll fix that. This room is terribly wired. It's so annoying. Yeah, it definitely does not capture everything. Anyways, so how can I use this string I came up with? I hate this thing so much. Come on. Why is it moving? Only the best equipment in Career. I think this is. What is it? It needs more slack or something. It's getting yanked on by the wire. That's very tilted. Anyways, any ideas? You can talk to me while I fix the camera.
So you're trying to arrive at the contradiction in that wait.
God, it looks so weird.
Picking I such that
Kills me.
the length isn't equal to 2 to some
That looks better.
power.
Yes. That's exactly it.
But I can't. But it's additive.
So let's think about, let's just take it step by step, okay? So I've already done, so A is barely a step, right? He fixed K and now K is just a variable that we don't know ahead of time, okay? I did step 2, which is the big one, but this one is actually super simple. Now the important thing is let's think about the third step, which is the adversary again, okay? So the adversary is going to split this up into ULV such that L is non-empty. Okay, so what is L? What are the adversary's options for how to split up Y? Y is just this. So
It could be anywhere from 1 to 1 to the K.
yes, it could be. It's some number of ones between 1 and K.
Yeah.
Right? Like the loop could involve 3 ones, and every time you see 3 ones, you loop. The loop could involve K ones, and every time you see K ones, you loop. The loop could involve a single one, and every time you see a 1, you just end up in the same state. And this is all just going to the same state. Does that make sense?
Yeah.
Okay. Now, why does that not... Now, how can we pick an I such that we ruin the adversary's day?
Do exponents on the lengths of words work in the normal way that they do in math?
W has to be in the language.
Like 2 to the m squared is the same as 2 to the 2m. Like it's a normal exponent, right?
2 to the m squared.
Is the same as 2 to the 2m.
2 to the 2.
Like exponents?
2 to, yes.
Yeah, okay, just checking.
But really we just need one fact. So let's, is W in the language? Yeah. W have to be in the language? In this case it definitely is.
I think, but yeah.
Yeah, it does, sorry. Okay, so W is in L. Boy. So what does K equal then? If it's in the language. If W is in the language, what does K equal?
A natural number?
Pick K. Oh, wait. So I can't actually. If W is in the language, you know what I have to do? I need to do.
You're saying that K is the pumping lemma number, right?
But K is fixed. I apologize.
Yeah, yeah.
So I need to adjust something, which is to say that. So I need to make sure my W is in the language. So X is going to be empty. Z is going to be, I don't know, 2 to the C minus K for some C.
Okay.
So yeah.
How does that make?
So think about it like this. X. Sorry, this needs to be Y.
Yes.
My bad. Good catch. W is this whole thing,
Okay.
right? So now it's definitely in the language, right?
Okay.
So. Oh, does it have to do with the fact that it's 2 to the m?
Could be 3 to the M. It's not that important.
Well, no, but it has to be at least, no it doesn't because if m is 0 it could be length 1.
So think about.
Are we saying that 0 is included in the natural numbers?
Yes.
Okay.
Let's think about this. Let's say I pick I in the last step. Why is this a good choice?
Then your string is length 3k plus 2c minus k, so it's 2k plus.
So then your string
2c.
is at so your string is, we don't know what L is, right? So
Yeah.
I'm going to erase all these weird DFAs because they're kind of in the way. So, the length of L, I mean L is between 1 and K, right?
Mm-hmm.
And K is going to be, we can pick the C, right? We pick whatever C we want.
Yeah.
So let's say 2C is greater. Okay, so this is not going to be negative because that wouldn't make any sense. Okay?
Okay.
2 to the C, not 2C. I apologize. Right, because we need it to be a power of 2 for W to be in the language.
Yeah.
Yeah.
Sorry. I think I meant to write 2C, but I just wrote it in the wrong place. Okay, so now let's just erase the K part and think about it like this. So our original string, x, y, z, is of length 2 to the m. It's of length 2 to the c, right? Which means it's in the language.
Mm-hmm.
Why is it bad if I now look at the string? Why is this string not in the language? X, U, L to the third power, V, Z. That's not in the language. I can be certain. Oh God, why do I keep writing C's down here? It's terrible.
just like calculate the length of the whole thing? See if that's a power of 2. Is that
Yeah.
what's happening?
Can this be a power of 2 in length? So, in fact, if this makes it easier to think about, I can actually just think about it like this. We only care about the length in this problem. So we know
We can rearrange.
this is of length 2c, right? Oh my god. Now what I want to do is I want to take 2 to the c plus size of L, 2 times the size of L, right? Because if I add 2 more copies of L into it, and this is the new length of my string, can this be a power of 2? Actually, a better way to do this is say, let's modify this to make it easier, because I actually just realized a thing that's going to be a bit of an annoyance if we pick, let's change it to 2, and we're going to set one extra condition about 2c. Let's say 2c is strictly greater than k over 2. Is that right? Is that what I want? Strictly 2c is strictly greater than k. That's what I want. So I just don't want k to be equal to 2c. This is a restriction I can set, right? Because k is fixed, and I'm picking c. So, yeah, I'm just going to set 2c, pick some c such that 2c is greater than k. Now this containment is strict.
Okay.
That's super helpful. And it makes math easier. So why is this not a power of 2? So what's the next power of 2 after 2c? 2 to the c.
2c plus 1.
2 to the c plus 1, right? So does this equal 2 to the c plus 1?
And the length of,
Hmm?
no,
It can't.
it can't.
It can't,
Can't.
right? Because the size of L is less than 2c.
Right.
We took something that was of size
Okay.
2c and added less than 2c to it, but at least 1.
Right.
So
So
it's
that's always going to be less than 2 to c plus 1, right?
Yeah.
Okay.
Right, because 2 to the c plus 1 is 2 to the c plus 2 to the c.
Yeah.
But this is 2 to the c plus something between
No,
1
it's not.
and less than 2 to the c.
Is it 2 to the c plus 2 to the c?
Because it's 2 to the c times 2.
Oh, I'm thinking 2 times. Yeah.
So it's 2 to the so 2 to the c plus 1 is 2 to the c plus 2 to the c, because that's 2 to the c times 2. Yeah, that's this one.
So
So let's now like back up and think about why this worked. Okay. The problem with this issue is that while DFAs can count, the loop is of some fixed size. So the first language was regular because the loop could be of the fixed. It was the distance between members of the language was fixed.
Yeah.
okay, thank you.
Yeah. Right. So when the reason you can't come up with a bad loop and be an adversary in that case is because they're going to make a loop of exactly that size, and they're going to be fine.
So basically,
This one, they are forced to come up with some loop, and you just exploit the fact that loop has a fixed size and thus can't accommodate this like ever increasing gap size or an ever changing.
Why does it have a fixed size?
Because the DFA is finite, which means the loop in the DFA is finite, which means that if you're trying to count something in a DFA, your loop if you're trying to make some counting like loop for counting, it has some fixed size. So it's going to like if I make one of those an accept state, then every time you end up in the accept state is some fixed distance from itself, right? So
that's a
like
critical
let's say
point.
there's like 4 things in the loop,
Yeah.
then I'm going to be in, and one of them is an accept state. Then I'm going to be in an accept state every 4.
Every 4 things.
Right. If we just are caring about string length, ignoring symbols
okay.
and stuff. This has an ever increasing gap in the membership of strings in the language, and a DFA is simply not flexible enough to deal with that. It doesn't have a way to count this kind of thing.
Okay.
Fluctuating gaps are very difficult for DFAs. Unless you can build some finite number of finite loops to count it, you're screwed. You could build a separate loop, one for 2, one for 4, one for 8, right? So But the problem is this one, there's infinitely many different gap loops
Mm-hmm.
that you would need, and so you can't do that with the DFA. So if I wanted everything that's, every string that's divisible by 2, 5, and 7, that's fine. If I want every prime length, I'm screwed. Does that make sense?
Makes a lot of sense.
Yeah.
Mm-hmm.
And you will definitely be able to exploit an almost identical thing for question 2, right? It has exactly the same problem. Let's do something that... So actually this one did use Z, right? X and Z are very flexible. They allow you to make the string in the language while still making a really artificial Y.
Is it uncommon to use all 3?
It happens.
Yeah.
I mean, I usually try and use X and Z as little as possible, I guess. But there's some really easy ways to use it like this, where you just take what's the way to put it? Let's say you want to count, so there's another problem. Do you mind if I erase this and I can do a separate example really quick? So let's go with the alphabet of binary, because we're familiar with that. And I want, let's come up with a new language, which is uh, 0 to the m, 1 to the m, such that m
That's not what we're doing.
right. Have you guys seen this before?
We did but A to the B, which is, or A and B, which
Okay,
is
so it's the same thing.
Yeah.
Let's do something slightly different then. This is slightly different.
Okay, when you come up with in a regular language, how do you think about it? Like, did you come up with this example?
I mean, I've seen this example before. It also has a problematic trait, which is that it's trying to count something and it doesn't know how big it is, right? It's trying, so normally if I was doing a program, I would have a counter for the number of zeros I saw. Then I would start deducting from the counter as I saw ones. And then if I stop seeing ones and I haven't seen exactly as many zeros or something, then I can do something. But that required me to store information about how many zeros I saw.
DFA's count.
And the problem is I don't know how many zeros I'll have to store. It could be far greater than the number of states you have.
Yeah.
So I could know that the number of m's is divisible by 3, but I can't know that it has 17 m's. If my machine has 17 states, then what if this is 24? It's
Because you have to be able to build a DFA for any M.
Yeah,
You can't just
for this
keep
language,
adding
yeah.
states.
Right. And so the way to deal with this is, okay, so they pick a K. I'll show another trick with this, which is, let's see. Fun fact about what? I. It's greater than or equal to 0. Picks I such that
Can be negative.
it can't be negative,
Yeah.
but it can be 0. Okay. Well, let's do. Okay, so no matter what K he picked, this is in the language, right?
Yeah.
Okay. What's a good I choice? So why is this? He has to split it up into some way. It's going to be exactly the same thing as the last problem, right? It's going to be some number of ones between 1 and K.
Just do 0.
You just do 0. Because now our string looks like this.
Oh,
Yep.
right.
0 to the K, 1 to the K minus 1.
Yeah.
0 to the K. Though actually, can I have 0 states? No, I can't have 0 states. The machine should have at least 1 state. I think size of K needs to be at least 1. Oh, k is just a number, actually, so I don't
Yeah.
need the size
Just
brackets.
as positive integer.
Greater than or equal.
Oh, so we have like the constraint on the size of y to be greater than k. So.
Yeah, so the size of y needs to be greater than or equal to k. That's why I picked.
Wait,
So this is in the language, right? No matter what k he picked.
Yeah.
And I'm going to be able to pick this y because it's defined by k. You're always going to have to define y somehow by k because you don't know what k is.
wait, why does 1k to the I become 1k minus 1?
Oh, sorry, it's 1k minus, however, it's something between 1
Well,
and k.
shouldn't it, if you have 0, if I is 0,
Yeah.
then you have k times 0 is 0.
So what you
1
have is this,
0
really.
is just
Let me write it out more explicitly.
0.
So this is x, right? This is z.
Yeah.
Then I want u, l, v here, which is just ones, right? But I don't know how many ones it is. So this is 1 to the, like, I don't know, I'm going to call this a, because I'm really, really out of letters. B, c, which add up to k. A, B, C add up to k.
Yeah.
And then I'm going to
But
remove,
you're only doing the one part.
I'm going to remove these.
Yeah.
And I know B has at least one 1.
Yeah.
So this is, this whole section, let's do it like this, is going to have 1 to the k minus b, where b is between 1 and k, right? And so these are not equal anymore, right? Because b is at least 1.
So it kind of depends if you're doing I onto the entirety of y or onto just L and y.
Yeah, I mean you are doing I onto L. I is going to only affect L.
Because in his, I see how they both work,
Mhm.
but in his, because then you just shift your k, but in his definition he has it that I is at the entirety of y, but it shouldn't really matter.
I like this form better. Let me look at his form and then talk about why his still works.
Because then you're just shifting your definition of his k, or his x and z is your xu and then vz.
So let's see. So pumping lemma for regular language is y. X, y. Size. Such that x, y is less than. X, y, z is an L for all. So y is not empty. Size of w is greater than n. So n is the size of the machine. That's his first step, essentially. Right?
Yeah.
That's the pumping length.
Yeah.
Then every string w and l,
Mhm.
which is us picking w,
Yeah.
with the size of w itself greater than n, we can separate it into x, y, z,
Yep.
such that y is non-empty. So this is actually the adversarial separation at this point, because notice that
Yeah.
y doesn't have to be greater than n.
Yeah.
Such that y is non-empty, so y is L in mine,
Yep.
right?
Yeah, that's what I thought.
Size of x and y together is less than or equal to n. That's interesting.
Because E can't be because X, Y, Z has to be included. Oh no.
So I would assume it should be size of x, y is greater than n. Oh no, it's less than or equal to n because there is a loop within n things happening.
Yeah.
Yep, okay, that's fine. Yeah, this is another way to define it. It has less letters. I think it is also less transparent as to what is happening. Like, yeah. I think while this does have more letters, I don't know if it maybe looks more intimidating. I find this more exactly matches up with like, yeah, let's see. So basically what he's saying is you can pick a string of length greater than the size, and there's a loop in there, and it happens within the first k transitions. right? So the way he splits it up, he's not dealing with any x. He's like, well, within the first k transitions, you only have k states. So there's a loop in there somewhere. And that's why he takes the size of x and y as less than n. Is because somewhere in that first n transitions, because his n is equal to my k, sorry, it's confusing, there must be a loop. And then he says, okay, and then he takes I. So you can also do it that way. This is another way to do it.
Just back to this example, like here we say that the length of L must be greater than 1. There we kind of took that out. We said that's going to...
Nope, we didn't take it out. That's why we know B is not 0.
Oh, so A and C are 0.
A and C can be... A, B, and C need to add up to... need to equal K, right? Because I'm splitting up Y.
Right.
Sorry, this is just me splitting up Y.
Right. So one of, like, either left or right is 0.
No,
So,
not necessarily. Like this could be 1, and this could be 2, and then this could be K minus 3.
okay.
Right? Because this is just the adversary splitting up Y. I don't know how they do it. All I know is that this B, because L needs to be non-empty, so this B must be greater than or equal to 1, but less than or equal to K.
I mean, if one of them is not 0, how are we equating that with K minus B?
So, because we set I to 0, that's why, sorry. So when we set I to 0, the only thing that disappears is a loop, right?
Right.
But that still throws off the whole equality, right? Does that make sense?
Yeah.
You still look like you have a question about it.
Oh, no.
You good? Okay, cool.
Process it.
Right. So yeah, you can pick I equals 0. You could also pick I equals 2, in which case you'd have 2b, and so it would be k plus 2b, and because b is 1 or greater, then that is all greater than k, and we don't have the 0m to the concatenated with 1m 0m structure, right? Ruins the structure. Let's see. Yeah.
For the third one on the P set, do you still use the pumping lemma? Because I feel like you do.
If it is not regular, you definitely use the pumping lemma. Which one is
I
it?
kind of feel like it is, though, regular. It's A and B star such that the word isn't a palindrome.
I think this one we can use like closure properties.
Yeah, because the complement
Yeah.
is just a set of words that are palindromes, and is that regular? Or is it not regular?
So, palindromes sort of relate to some of the languages, regular and not regular, that we talked about now. So, let's talk about how you build code in like a computer that checks this. Or like if you were doing this by hand, what are you doing? Because that actually helps a lot, because it tells you what you would need to do, like what you think you would need to do to check if something's a palindrome. Then you can think about that process, and you think, does this process equate to something a DFA is capable of? Because there's things like that I'm talking about, like, regular gaps, very DFAable. Non-regular gaps, not DFAable. This, checking some unbounded, keeping some unbounded counter, not DFAable. Keeping a counter, DFAable.
Probably not.
Why? So what's the process? So just describe the process of checking if something's a palindrome. How would you maybe do it? Using code.
I mean, could you do something? I mean, I don't know code.
I don't know code either.
Okay. What
But it just has to be a strategy. Like you could do it on paper.
Could you just start like two separate, no, I guess you can't do that. Like you can't start at the beginning and then start at the end.
You could.
And see if you can meet in the middle.
I mean, you could write, that's one way to do it. One way to do it is you look at the first character, you write it here, and then you look at the second character, and you write it here.
Yeah.
You look at the third character, write it here, look at the fourth character, write it here.
Yeah.
And then check if they're equivalent. That's one way to do it. You could count the length first, right? And then make a list and now let's say I was length 10.
But
Well, certainly if it's odd, you get rid of you
Yeah.
say it's not a palindrome.
Yeah.
Well, actually, no, odd is fine because the middle thing always matches itself.
Always matches. Yeah.
Right, sorry. I was thinking of something else. Okay, so let's say though this has length 10, then
But isn't that the problem, like knowing the length of the word?
Yeah.
That-
For end?
does seem problematic already. And then now what I would do is I'd go in reverse and I would cross them out. Like I would see, okay, I see a 1, so I cross this out. I see a 1, I cross this out. Oh, I see a 0, it's not a palindrome.
Yeah.
Something like that. But yeah, so I just, in my strategy at least, seems to be an unbounded count.
Yeah. It seems kind of like the example of like 0 to the m, 1 to the m, or like a to the m, b to the m, such
Okay.
but that a and b are strings because they have to match each other.
So one helpful thing when you don't know if a problem is true or not, like one way or the other,
Match each other.
is to bounce back and forth between the two hypotheses
Yeah.
and try and make advances on both. When you try and prove it's regular, you'll notice reasons that it seems difficult, and then you can try and leverage those
Okay.
in a pumping lemma proof
Mhm.
to show that it's not regular. And then if you find you're getting stuck, you're like, oh, the adversary seems to keep beating me because they can loop in these locations. Try
Right.
building those loops, you know?
Okay.
And because, if you tried to prove that like the 2 times k, like the all strings of even length, was not regular, the problem you'd keep having is that the adversary is going to pick a loop of length 2.
Yeah.
And what does that tell you? It tells you should build a machine with
Yeah.
a loop of length 2, right? Which is exactly the answer. And so bouncing between the two can be helpful. What was I going to say?
Does AB star mean that it has to have a and every string has to have an a and a b in it?
AB star means it's either A or B, and it's basically the list of all binary strings. It's the language of all binary strings except you've replaced A with 1 and B with 0 or something. W is just a string of A's and B's at that point.
Oh, okay.
Because
Okay.
star of A and B means
Mhm.
I have any number of
A's and any number of B's.
any number of characters in a row
Mhm.
that are either A or B. That's the way to think about it.
Yeah. Okay.
It's k copies of elements from the set
Okay.
A B.
Okay.
Which is just every string of A's and
Every
B's.
string
It's
of
a
A's
little
and B's.
contorted, but you see why that works? Like if you star, like if I take 0 or 1, 0 union 1, I should say, the set of 0, oh my god, this is so annoying. Set of 0 and 1. This is almost like a clearer way to see it. It's like star this, then it's either this or this each time, and I can do that any number of times. Something like that. It's something like that. Okay, right, so it's basically all binary strings except they're A's and B's instead of 1s and 0s.
Okay.
But so let's think of a terrible pumping lemma proof, because it's actually not going to work. This particular approach is, let's say that I pick, so at least this W choice sucks. Let's pick the string of, so now we're talking about the palindrome problem. Let's pick this string. Why was this a horrible choice? So I'm gonna say W equals this, and I'm gonna break the. Do you mind if I erase this example and actually just use this? I like this chart setup. I'm gonna say. Empty set, 1 to the k.
That's always a palindrome.
That's always a palindrome, right? So this is okay. So this satisfies all the things I need to do in part 1, right? I need to pick something that is at least of size k, and I need to make sure that it's in the language. This satisfies those things, right? Cool. Now the adversary is going to pick some substring in here, and I'm going to try and pump it. Am I going to be able to not make it a palindrome? No. This is a failure.
Yeah.
So this is already appearing to be if this is non-regular, this is already a more difficult problem in some sense than the other ones, right? But now, the next step, so like I was saying, you can bounce between the two. So if this doesn't work, can you pick a more complicated W that will allow you to break it? Because this one certainly doesn't work. It's too uniform. There's something about it that's just wrong.
If you have 0s and 1s in the Y, like.
So remember, Y though has to be of length k, so we need to define it somehow in terms of that. So we need to define Y somehow with respects to k.
order for it to, and it has to be a palindrome.
Has to be a palindrome.
So like 1, 0, 1 each equal parts of k, but that assumes k is divisible by 3.
You could define it two ways. One where you could think about defining it with respect to like, okay, here's how I define both sides. No problem. Have a good one. Here's how I define both sides, and then like if it's an odd length string, I just put a 1 in the middle or something. I don't know.
Okay.
Like if you were thinking, 1 to the k, 0, which let's say it's 1 or 2 zeros, depending on whether k is even or odd.
Yeah.
So it's either this or this, but this one might not be there.
Yeah.
And then 1 to the k,
One
right?
to
That
the K.
seems fine.
Yeah.
Okay. So that's one option. So you like I see what you were saying, and but you can get around that problem by just being a little careful.
Okay.
Yeah, I mean, so this is a palindrome, right?
Yeah.
And it's definitely bigger than k. This is either going to do one of two things. It's going to prove that it's not regular, or it's going to tell us how to make a loop to deal with these sorts of cases, right? So those are both good.
Okay.
I'm going to leave soon.
Yeah,
but,
yeah, sorry.
Well, no, it's fine. I'm generally happy to stay for quite a bit extra. As long as, I feel like it's helping people, I don't mind. So, yeah, what are the adversary's options for L, right? Because let's, do we want to deal with X and Z? Do we want to pick stuff for X and Z, or do we want to just make them empty?
Probably just empty.
Yeah, for now we can leave them empty, I guess, right? We can always go back and change it.
Yeah.
But
Or it might be helpful to have I could see that it would make sense to have Z, have them not be empty, because if you're only extending, maybe the thing to do is make X and Z different sizes, such that the ones on the end between the 0 or after the zeros are different sizes.
Yep, that's a good idea.
So then when you're repeating it, those two sides get to be different sizes.
Let's try this one, and then because
Okay.
if this one doesn't work, that is a good idea. I completely agree that makes a lot of sense, and it's a clever way to use X and Z because it's like it feels like they should have to be the same,
Yeah.
but technically they don't actually have to be identical, because you can put
that's true.
more of X into Y,
Yeah,
right,
yeah.
and then
Okay.
without doing that for Z, and that's a good observation. But yeah, can we try and pump this? So what are L's options? What are the adversary's options for L? Can we break it into cases? Because before it was one case really. It was like anywhere from 1 to k.
Yeah.
Ones. But here it feels like they have some actual choices that matter, right? Because
Yeah. It could be just a 1. It could be 1, 1.
it could be just ones, right? It could be like the previous case.
It could be just the first component.
So it could be just the first component of ones, right? It could be just the second component of ones too. And then what's the other option?
It could be it could be the full Y, or it could be with 1, 0, and then all the sets of first ones with the 0, or the second set of ones with the 0, or any portion of that. So yeah, basically. And let's see. So pumping either side of ones is gonna fail for it, right? Like if we put I's, if we increase I, if he just picked L as ones from either side, It fails.
then we win.
Yeah.
So what about if he just picks 0?
The 0, then we lose.
Then we lose.
So it's if you're only
So we can go back to
one element.
So now we can try your trick and see if that helps us, right? So
Okay.
let's say this is how best to
Because it's
do
for
this.
all I, or all L. Yeah, okay.
I don't know, let's make this 1 1, make this 1 1 1 1 or something.
Yeah.
Doesn't seem to help us, right?
No, it doesn't.
Because you can still do the same thing with the zeros in the middle.
If you had. Wait, but why? Oh, because you can choose any L. He can have any L be the subset.
Right. So he's picking
Okay.
the 0 in the middle to take advantage of your scheme.
Okay. So then if you shift all the ones over, that would still work. So maybe it is
So,
regular.
Yeah, that's one option. Why does this keep failing though? What is the adversary taking advantage of here? I mean, whether even if it's regular, we want to figure that out, right?
Yeah,
Because
yeah,
then we
yeah.
want to exploit it, because we'll need to use it to build a machine, essentially.
That you could have a loop, like one loop over and over again.
But why does the loop work? Like, where in the string location-wise is he picking that
The
works? Because
middle.
this did the exact middle, right?
Mm-hmm.
Does the middle? Okay. Why does that help us? Why is that? That's extremely useful information. And I would think more about your uneven choices of x and z more.
Wait, but is that even a palindrome?
Yeah.
If K,
So-
they're not the same number on either side?
Yeah. Oh well, they're the middle. So if there's not the same number on either side, you're defining
but
the
your
string.
your y
It's,
accounts
yeah,
for
but your
that.
y doesn't have to be in the middle, does it?
No.
Does it have to include any characters from the middle?
So you just do it all, like ones from the beginning or something.
So let's try another tactic. Why don't we start from scratch and you can give me an x, y, and z, and we'll see how it goes.
Okay. So if you have x is, I don't know, the empty set, I think would work.
Okay.
And then y is just 1 to the k. No. Yes? Well, let's see. Z is, I don't know, 0 and possibly another 0 and then 1 to the k. Then for any I, that doesn't work.
You have to be a little careful with the 0 again, right?
Yeah, possibly. Cool. Okay. Then for all i's it fails.
Yeah. Okay.
So then
you
it's
just
not
solved it.
regular.
Yeah.
Okay.
You just solved it. And it makes sense why, right?
Nice. Yeah, that makes sense. Ah, this is fun.
And it takes advantage of essentially like this same problem where we paid attention to the part it was like trying to count essentially.
Yeah.
Like not only can it not deal with palindrome, it can't even figure out how long half is.
Yeah, I know. That's what I was thinking about the half.
Right.
Okay, cool. Nice.
So hopefully that helps. Pumping lemma
Yeah.
is the last thing that will be on the midterm.
Oh,
So
okay.
your hardest
okay.
question should be a pumping lemma question.
Oh, okay.
And I think this game,
Uh-huh.
some people like his game better, and you definitely can think about it and translate between the two. I personally, it looks like more letters should make it more frightening. You can just forget about some of the letters if you want. It allows you to kind of use the entire structure of
Yeah,
the
that
string
makes
if you
sense.
feel like you want to. Whereas with his, you kind of end up sometimes going deeper into those single variables and splitting them up anyways.
Yeah.
This just explicitly splits them up from the get-go.
Yeah, I feel like this makes it more rigorous, kind of.
Yeah.
You're splitting up y even more.
Yeah.
Cool.
I personally prefer this one. I actually learned the other one first and I found this one really weird, but as soon as I understood it, I was like, oh, actually.
Nice.
Alright, great.
Cool.
Hope that was helpful.
Yeah, definitely.
So nothing after the lecture from yesterday will be on the midterm.
And it's next Wednesday, right? The midterm?
Yes, the midterm is next Wednesday, so there'll be an office hour on Monday and Tuesday beforehand.
Okay, cool.